Before iron ever became a beam, a bolt, or the hull of a ship, it was locked inside. Mountains like these? For millions of years, the ore sat buried in layers of rock. Then humans arrived with drills, explosives, trucks, and furnaces. Today, those mountains are broken open by controlled blasts, loaded into giant haul trucks, and sent through a chain of machines that turns raw stone into one of the most important materials on Earth. Iron holds up our cities, strengthens our vehicles, builds railways, bridges, ships, tanks, factories, and machines. It even helps carry oxygen through our blood. Without iron, the modern world would slow, almost instantly. In this journey, we follow iron from an open pit mine to a processing plant, then across railroads and ocean ports, into a blast furnace, through a rolling mill, and finally into finished bolts and steel parts. To understand why this metal matters so much, we have to start with its nature. Iron is abundant, strong, recyclable, and, when heated to extreme temperatures, it can be shaped into almost anything. At about 1,538 degrees Celsius, solid iron melts into a glowing liquid. That change is the beginning of modern steelmaking. This is not just a factory tour. It is the path from geology to civilization, from buried ore to finished steel. One reason iron dominates heavy industry is that it can return to the production cycle again and again. In the United States alone, tens of millions of tons of scrap steel are recycled every year, giving old cars, beams, tools, and machines a second life. But before steel can be recycled, the story begins underground. Iron makes up a large share of Earth's crust. And in places like Minnesota's Mesabi Iron Range, the deposits are big enough to support mining on a massive scale. At the Mintac operation, more than 10 million tons of iron ore can be processed in a year. From the rim, the mine looks less like a workplace and more like a man-made canyon cut into benches and layers. Crews first strip away waste rock that covers the ore. Then they drill, blast, scoop, and haul the material deeper into the operation. A mine like this does not sleep. The demand for iron is constant, so the machines keep working day and night. But this ore did not simply appear in the ground. Long before humans existed, iron was created inside ancient stars. When those stars died, explosions scattered heavy elements through space. Some of that material became part of the young Earth. As the planet heated and separated into layers, much of the iron sank toward the core, while a smaller but still enormous amount remained trapped in the crust. In places, the pit stretches roughly a mile wide and thousands of feet long, with several ore layers exposed like pages in a book. In Minnesota, that crustal iron slowly became concentrated into ore bodies. Water, oxygen, pressure, and time helped shape the deposits that are mined today. The ore currently coming from this region is mostly magnetite, an iron oxide with a lower iron content than the richer hematite once pulled from the
range.
Hematite could contain much more iron, but decades of heavy demand, especially during the World Wars, reduced many of the richest reserves. That is why modern mining depends on upgrading lower-grade magnetite. The work begins with force. Drill holes are packed with explosives. The rock face is blasted apart, and the broken ore is loaded into enormous haul trucks. These trucks are almost the size of a house and can carry up to 240 tons in a single trip. From there, the ore heads to the processing plant. Crushers break it down. Grinding mills reduce it even further until the rock becomes fine particles. Water is added to turn the material into a slurry, a flowing mixture that can move through pipes and separators. Then comes one of the most important steps, magnetic separation, where useful iron begins to pull away from ordinary waste rock. The magnetite being mined can sit near 22% iron. while old high-grade hematite could reach roughly 65%. The trucks themselves measure several meters, tall and wide, built for a mine where every load matters. Inside the separator, a rotating drum carries powerful magnets. As the slurry passes through magnetic iron, particles cling to the drum, while non-magnetic impurities wash away. It is a simple idea working at industrial scale. Use magnetism to separate value from
waste.
The result is a richer iron concentrate. That concentrate is mixed with a binder and rolled into small pellets, each roughly the size of a marble. These pellets are easier to handle, transport, and feed into a furnace. But pellets are still only the beginning. To make steel, producers must remove impurities, control oxygen, and carefully manage carbon. In the blast furnace, coke provides both heat and chemistry. Carbon reacts with the ore and helps release metallic iron. Too much carbon makes the final metal brittle. The right amount gives steel the balance of strength, hardness, and flexibility that industry needs. From that iron-carbon base, engineers can add other elements to create specific grades. Today, computer modeling helps steelmakers design advanced high-strength steels for vehicles, buildings, and machinery. Some grades can be several times stronger than conventional steel. The point is simple: without iron ore, there is no steel, and without steel, modern society would look completely different. Since the early 2000s, major automakers have relied more heavily on these advanced grades to make vehicles lighter, safer, and stronger. From the United States, the story moves to Australia, where Rio Tinto operates some of the largest iron ore mines on the planet. Many of its Pilbara sites are so remote that workers fly in for their shifts, crossing huge distances before they even reach the mine, moving hundreds of millions of tons of ore from desert pits to the global market. It takes more than trucks and excavators. It takes a complete logistics system built at extraordinary scale. Rio Tinto operates a rail network stretching roughly 1,900 kilometers across Western Australia, connecting mines to export ports. Even the rails used in this network are prepared with precision. Short rail sections, each about 25 meters long, are fed into a flash butt welding line. Electric current heats the rail ends until they soften, while pressure forces them together into one continuous piece. This method creates a strong, clean joint, suited for heavy haul trains. Traditional welding can leave weak points or defects, but flash butt welding produces a more reliable rail. Workers repeat the process again and again until many short sections become long rail strings ready for the outback. The finished rail strings can reach hundreds of meters long enough that moving them requires coordinated cranes and purpose-built rail cars. After welding, cranes lift the long rail sections and load them onto special transport cars. A single lift can move an impressive length of rail. A reminder that every part of this system is oversized for one purpose: moving ore. Out on the line, a typical iron ore train may use 3 locomotives and hundreds of
wagons.
Fully loaded, it can haul about 30,000 tons at once. Many trains operate autonomously across the Pilbara network, while remote control centers track their movement from far away. In rail yards, or when something goes wrong, a driver can still take manual control. Keeping this fleet alive is another huge operation. The maintenance base houses hundreds of diesel-electric locomotives. Engines come in for inspection, refueling, and service on a constant schedule. The work continues 24 hours a day because the supply chain depends on rhythm. Mines feed the trains, Trains feed the ports. Ports feed the ships. If one link slows down, the whole chain feels it. Some facilities manage more than 220 locomotives, with full inspections every couple of days. Because a stalled engine can hold back thousands of tons of ore. When the ore reaches the coast, the next challenge is unloading it quickly. At Cape Lambert, one of Rio Tinto's major export ports, loaded trains roll straight into the unloading system. The key machine is the car dumper. It clamps 2 rail cars at once, rotates them, and empties the ore into hoppers below. A full train can be unloaded in about 3 hours without separating every wagon. Rotary couplings allow selected cars to turn, while the rest of the train stays connected. This saves time and keeps the flow moving. From the hoppers, conveyors take over. The ore moves from belt to belt, leaving the train behind and entering the port system. Beyond the conveyors is the Indian Ocean. Beyond the ocean are steel mills waiting for raw material. At this stage, the ore is no longer just a product of a mine. It is part of a global supply chain, timed, blended, and shipped to match demand on the other side of the world. On average, each car is emptied in less than a minute, which is why the unloading system is as important as the trains themselves. The stockpile yard at Cape Lambert works like a giant blending kitchen. Conveyor belts carry ore across the site, some only a few meters long, others stretching for kilometers. Stackers build towering piles from train load. After train load, a single stockpile can hold around 200,000 tons of ore. But these piles are not simply stored and forgotten. Different mines produce different grades, and every steelmaker wants a blend that matches its furnace and product requirements. That is where the reclaimer comes in. It cuts into the stockpiles and feeds ore back onto conveyors in carefully controlled amounts. By drawing from different piles, the port can create a custom mix for each customer. During rail transport, stockpiling, and conveyor movement, some ore breaks into fines. For premium shipments, those smaller particles may need to be screened out before loading. The goal is consistency. A steel mill cannot afford surprises inside a blast furnace, so the ore must arrive with predictable quality, chemistry, and size. The site can handle many ore types at once, fed by multiple mines, and its conveyors form a moving network of steel belts, transfer towers, and stockpiles. After screening, the ore reaches the last stop in the export chain, the ship loader. Cape Lambert extends far into the Indian Ocean and can handle several bulk carriers at once. Shiploaders swing over the open holds and pour ore into the vessel layer by layer. A large carrier may take about a day to load and can leave port with around 180,000 tons of iron ore on board. From Australia, that cargo sails to steelmakers around the world. One of them is POSCO in South Korea, among the largest and most productive steel producers in the industry. At its private port, ships unload iron ore, coal, and other raw materials. Huge grab buckets lift ore from the cargo holds, while support machines keep material feeding into the system. Even with heavy equipment, unloading a ship takes time. Once ashore, the ore rides conveyors into the raw material yard. it may still look like ordinary rock. But from here, the transformation becomes far more intense. The offshore terminals extend kilometers into deep water, where multiple ship loaders can work around the clock on several vessels at the same time. Before ore enters the furnace, fine particles are sintered into larger, stronger pieces. This helps air and gas move through the furnace and improves the quality of the hot metal. At the same time, coal is converted into coke. It is heated in oxygen-free ovens at extremely high temperature until it becomes a hard, carbon-rich fuel. Coke is then pushed from the oven, quenched, cooled, and prepared for use. In the blast furnace, layers of sinter, coke, and other materials descend from the top. From below, intensely hot air blasts upward. Inside, carbon monoxide forms in strips. Oxygen from the iron ore, leaving metallic iron behind. It may look like chaos, but the process is controlled chemistry at enormous scale. At the bottom of the furnace, molten iron collects and flows into a ladle. Above, it floats slag, a lighter byproduct, made from impurities and flux. Before the metal can become high quality steel, that slag has to be removed. The coke ovens can reach around 1,000 degrees Celsius. And the hot blast entering the furnace can be even hotter, driving the reactions that separate iron from oxygen. In the slag treatment area, the hot metal arrives glowing orange and gold. It is beautiful to watch, but the danger is obvious. Machines scrape the slag from the surface and collect it for reuse in materials such as cement or asphalt. After that, the hot metal goes into refining. The chemistry is adjusted again and again until it matches the target steel grade. This is where steelmaking becomes both science and discipline. A small change in carbon, oxygen, or alloying elements can change the final product completely. Once the molten steel is ready, it is poured into continuous casting equipment. Instead of making one giant block, the caster cools the metal into long billets that can be cut, marked, and moved. Water sprays, rollers, and cutting machines run constantly. The billets are reheated, cleaned with high-pressure water, trimmed and cut to length. Product codes are marked on the ends, so every piece can be tracked. Then electromagnetic cranes lift the billets toward the next heating cycle, where rolling will turn them into new shapes. This casting and cutting line runs continuously, with cooling water, sensors, cranes, and operators keeping the glowing steel under control. After reheating, the billets enter rolling stands that squeeze and stretch the steel into long wire rods. These rods may later become bearings, tire, cord, springs, fasteners, and many other industrial parts. When the rods leave the mill, they are still glowing hot. They cool, coil, and get bundled into heavy rolls that can weigh around 2 tons. Some of those coils are sent to a bolt manufacturing plant. There, workers trim the rod ends so the material feeds smoothly into the machines. The wire rod enters a header where it is cut and forged into the rough. Shape of a bolt. At this stage, the bolt has a head and body, but no thread. Thread rolling comes next. Hard dies press into the blank and form the spiral ridges without cutting away metal. Nuts are forged in a similar way. After forming, bolts and nuts go through heat treatment. Oil residue is washed off. The parts are heated, quenched in oil, cleaned again, reheated, and cooled with fans. This gives them the strength and stability required for real-world use. Finally, electroplating adds a protective finish, often silver or black. POSCO has also set a long-term goal of moving toward hydrogen-based steelmaking, a sign of how this old industry is still changing. The 2-ton coils leaving the mill become raw material for smaller factories. Downstream. After plating, the parts are dried, matched, and assembled into finished bolt and nut
sets.
Cameras inspect each piece, checking shape, surface quality, and fit before packaging. What began as iron locked inside rock has now passed through mines. Trains, ports, furnaces, rolling mills, and factories. In the end, it becomes something small, precise, and easy to overlook. A simple fastener with a powerful job, holding the modern world together.